In this video, we will dive deep into Monte Carlo simulation, a technique much older than Excel. It goes back to the modeling of casino games in Monte Carlo, where they were dealing with games that were too complex to model mathematically. But they figured out if we will play the game many times, either roll a lot of dice or draw a lot of cards or spin a lot of roulette wheels, and keep track of the results, then we can find out kind of what our expected result is and what the range of outcomes might be. I've applied it to the course grade model here. If I thought my final exam score were going to be somewhere between 75 and 95 and most likely around 85, then I could run it through the course grade model many times, sampling a final exam score and calculating the corresponding course grade, and do that so many times that I eventually get a distribution of course grade. And I realize pretty unlikely I'd make less than an 85, pretty unlikely I would make more than about a 91 or so. And that's the idea of Monte Carlo simulation. To use it in Excel, we rely on two primary concepts. One is that Excel can generate a random number using rand or rand between. And two is that Excel can recalculate our model repeatedly using a data table. So we'll use these ideas to do Monte Carlo simulation in Excel. Let's do a simple example now. Let's say you had a team of 3 people, and they're going to play a game where they select a number between 1 and 10. Let me show you what that looks like with a formula text. And so each time Excel recalculates, all 3 of these people are selecting a number between 1 and 10. Watch, when I type the word average and hit tab in this case, or enter, Excel's going to wonder, well, did that affect the rest of my model? I'd better recalculate the whole model and see. And when it does, it comes up with different random numbers. And then when I put it in a formula, once again, when I hit enter, Excel is going to recalculate the entire spreadsheet, including these random numbers, and get new answers. So anything we can do to make Excel recalculate, by the way, F9 makes Excel recalculate, so when I hit the F9 key, anything we do like that will give us new random numbers and a new average. So these aren't really model inputs. These are actually model calculations, and this is a model output. So in this case, we don't technically have model inputs. Suppose our model inputs would be 1 and 10, because those would be the values we could change. I broke a modeling rule for this video and used a number where a reference would work, but I think you'll appreciate me saving the time. Now let's think about how, besides hitting F9 over and over, we could trick Excel into recalculating over and over. One way is if I had a model that said 2 plus 2 is 4, and these were inputs, and this was an output. I could build a data table that said, well, 2 plus 1 or 2 or 3 or 4 or 5 is what? And so my output is here. So this is the sum. And I think they call these add-ins. So if I were to build this data table to put each one of these numbers here and see what happened to this number, I could see what 2 plus each one of these numbers was. That's not very exciting, but I could grab another output. Remember, with a column data table, I can have as many outputs as I want. And so another output I might want might be average. So let's pick up this one, format it as an output, rebuild our data table. And we've used this data table to trick Excel into running 5 times and giving us 5 different samples of these numbers between 1 and 10. And so we got 5 different answers over here. And if you think about it, we really didn't even need this model to do that. All we were doing was putting a 1 in this cell, and a 2 in this cell, and a 3, and that caused us to get what we wanted over here with the outputs. For example, if I get rid of one of these inputs, I could even get rid of the output. I could even delete this cell. And this is still working. I'm putting a 1 over here and causing it to recalculate, a 2 over here and causing it to recalculate. And each time I get a new average from the team selecting their numbers between 1 and 10. So I don't even need this column, but a data table has to be contiguous. So let me delete the data table, delete the column, and then rebuild it. Again, saying put these numbers in this cell. That's not an add-in anymore. Let's call it an iteration, because I'm really getting 5 different iterations. Every time I put a number in this cell, then I get a new average. And so this cell doesn't have to be here. It could be anywhere else. The only place on this spreadsheet that I feel really safe putting it is a cell that I know is never going to be needed for anything else. And that's this cell right here. So what I'm going to do is color that yellow, delete the contents because it really doesn't matter what's in it. We're going to plug these numbers in it when the data table calculates. And I'm going to move it up here. And so we call this data table on a blank cell. We've got a data table. We're putting the inputs in a blank cell. And we're grabbing the outputs from something that's based on random numbers. We are running Monte Carlo simulation. Let's delete this data table and do it on a larger scale. Let's say this time I want to run 20 iterations. I'll also go ahead and pull out the random number that Ali picked, that Bob picked, and that Charlotte picked, and bring in the average. That would have been a good time to say copy, paste special, and transpose, wouldn't it? Now to create the data table, we're going to call these our column inputs, even though it really doesn't matter where they go. And we know we're going to put them in a blank yellow cell right here. And then we'll take Ali's guess, Bob's guess, Charlotte's guess, and the average out of our model. Let's treat all those as outputs for the data table purpose and run the data table. So again, we've got a column of input cells. There's really no input in our model, so we're just going to put it in the blank cell. Hence this process is called data table on a blank cell. And when we run the Monte Carlo simulation, we see a whole lot of outputs. This list of numbers is what's used to make this histogram coming out of our model. So let's make that histogram. The histogram says bin this data and draw a bar chart of it. So if I wanted bins 1 through 10, because my average can't be less than 1 or greater than 10, and tell me how many of these outcomes, of these 20 outcomes, tell me the frequency here for each bin. Now Excel has a frequency function that says point at the data array and the bins. And if your version of Excel is new enough, that's all you have to do. If you're in an older version of Excel, you have to enter it as an array formula. Contact me for help on that. So now we've got our frequency of bins, and really this one is greater than 10. And we can make that into a picture by selecting these cells, doing an Alt NC1, which brings us to the 2D column chart. Add our axis titles to show frequency versus bins. And in this particular simulation, we had a couple of numbers that were greater than 3 and not greater than 4. That would be this one and this one. We had 5 numbers that were greater than 4 and not greater than 5. 1, 2, 3, 4, 5. We had one iteration where the average was greater than 8 but not greater than 9. That's probably this one. And then no iterations where the average was greater than 9 or greater than 10. And just like before, each time I hit the F9 key, it recalculates the spreadsheet, or in this terminology, reruns the Monte Carlo simulation. So F9, 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 F9. And you notice the character of the chart changes each time I run it. We've only asked the team to make their guesses 20 times. I'll bet if they guessed 1,000 times, then this would average out to be more of a repeatable shape. We'll try that in a moment. But first, I also want to point out that regardless of the shape, it always tends to have more answers in the middle, or toward the middle, than toward the ends. It's incredibly rare. I guess it would be about 1 out of 1,000 times if everyone were to select 1 or everyone were to select 10. But if some guess high and some guess low, then things tend to average out in the middle. So we end up in the middle a lot more than we end up on the ends. If you want to learn more about that, Google the central limit theorem. But what I'd like to do right now is ask the team to do 1,000 iterations instead of 20. So I'm going to delete the data table again. I'm going to copy this down to 1,000. Overshot a little bit, so I'll back up to 1,000. And now I want to rebuild the data table. Again, the column input cell, the iteration, just goes in this blank cell, doesn't get used. Now my frequency formula is still just binning the first 20. If I wanted to go all the way to the bottom, I'd have to control down, see that it was on row 1002, and change this formula to go down to row 1002. Now look what happens. I get a much more repeatable shape of the distribution because we're running our model many, many more times. Every time I hit F9, it changes a little bit, but not a lot. And so one way we could think about how long it takes that model to converge is what we're saying. So let's think about overall, over the long run. If I highlight that column and look down here, our average is 5.5. If they did this an infinite number of times, we'd expect it to eventually converge to 5.5 exactly. It got to 4.85. Let's see how long it took it to get there. Let's look at a convergent. Actually, let's call that a running average. And if I would write a formula that looked like this, if I want to average that number where I lock the first one with absolute references but not the second one, and then copy that down, look what that does. On the first one, I'm just averaging the first iteration. On the second one, I'm averaging the first 2 iterations. On the third one, I'm averaging the first 3 iterations, and you get the idea. So if I plotted the number of iterations versus that running average, I should get a pretty good picture of how this thing converges. So I'm going to click, Control Shift down, Shift F8, or I could Control click, Shift, Control Shift up. Now I've selected 2 non-contiguous ranges. I could do an Alt-ND to go to Data and insert a chart. And then I like this one that comes up automatically. It's an XY scatter chart. Please don't call me if you choose the line chart and this thing doesn't work for you. You need to use an XY scatter chart by going to this button right here. And we'll get the one without any lines in between. And look what happened. That first couple of iterations, we wouldn't expect it to be anywhere near the long-term average. But very quickly, this model converged. It only took less than 100 iterations, and it had pretty much zeroed in on that 5.5, plus or minus a little. We probably didn't need to run 1,000 iterations. Computer time's cheap for us, but if we were paying for computer time with a terribly complex model, we'd want to be real careful about how many iterations we ran. And in this case, I'll bet 50 or 100 would be plenty. We'll call this convergence, where we plot running average against iterations. Now, when we get into more complex financial models, it will take more than 50 or so iterations to run. In fact, sometimes 1,000 may not be enough. If this thing is still trending or moving around, there are much more complicated ways to decide how many iterations to run, but for this class, we're going to use this chart and our gut feel. Let me abbreviate that so I'll have space on this sheet to show what it would look like to do a percent rank. And this says, of all the possible outcomes, where did this one rank? We can use percent rank the old school way, or excluding the extremes, or including the extremes. I think for this class we'll include the extremes. We don't care what that means, just use percent rank.inc. And it says give me an array, and be sure to put absolute references on the array. Give me the data point of interest, ignore significance, and I will tell you how this one ranks. So 8 ranks very high, very close to 1 in all the possible outcomes. 2 ranks very close to 0 in all the possible outcomes. So if I have this column selected, hold down my control key and click on this, do a control shift down, which also works on a Mac. Scroll the window back up. I can plot these by doing an Alt-ND, which takes me to data, and then to insert and XY scatter chart. If you try this with a line chart and it doesn't work, please don't call me. Just go back and do it with a XY scatter chart. And you'll see a really nice curve showing the probability of getting an outcome less than this average. So there's about a 50% probability that would be less than 4.5. There's only a 20% probability that would be 5.5. Only a 20% probability that would be less than about 4, and a minute probability that our average would be less than 2. Similarly, we're almost certain it's going to be less than 10 or 9, let's say, and maybe we're 80% sure it will be less than about 7. So we'll call this a cumulative probability chart. We've done 3 types of charts: a frequency, a convergence, and a probability chart. And the only thing left to do is add a couple of lines to the cumulative probability chart. I'd like to add a goal line that says if I have a goal of reaching an average of 8, what is the probability of achieving that goal? And the other one is if I want to talk about value at risk, like finance people do, as a 95% or 5% worst possible outcome, depending on your perspective, then what is that worst possible outcome, or near worst possible outcome? To add those 2 lines to this chart, we're going to need 2 columns. One of them is going to be the actual average that we're talking about. That'll be our X data, and the other one will be our Y data. We'll call that probability. We're going to want that for the goal and also for the value at risk line. Now for the goal line, we need to know what our goal is. So let's say we have a goal of 8, and since that's something that we're choosing, I'm going to format it as an input. And let's say for the value at risk, we know the probability is going to be 95%, or in this case we'll use 5 because a low average, we've been talking about being kind of negative. It really all depends on your perspective. If you're trying to minimize cost or maximize profit, then it could be at one end or the other. But in our case, the probability we're interested in is 0.05. And we'd like to see what averages go along with that. So I want to fill in these 6 cells and these 6 cells in order to have the dots that I need to put these lines on the chart. Now for the goal, we know that if we have a number that we want to convert to a probability, that's the same thing we did in column M, and that formula, column N, and that formula was percent rank dot inclusive. So I'm going to say percent rank dot inclusive of all these possible outcomes. Control up, start on the first one, control shift down, go to the last one, and then hit my comma. Now look where I am. I'm on row 1000 and I need to get back to where I am. So if I'll just hit the up arrow, it will take me back up here to where I'm writing the formula in a cell up. Actually, I wanted to go left. So percent rank dot inclusive of all the possible outcomes, and then comma my goal, tells me that I have about a 91.5% chance of being less than that. That means if I ran this thing 100 times, chances are 91 times out of 100 I would be less than the goal or miss the goal. So we have about a 91% chance of being less than that goal. Now when we calculate probability of success, it's not really 91% chance of probability of success. It'd be 1 minus that. But for the goal line, where we're using this less than axis, this is okay. If I want to draw a line from 8, 0 to 8, 0.912 to 0.912, then this is going to be equal to that cell. This is going to be a 0. This is going to be a 0. And this is going to be equal to that cell. Probably doesn't make much sense until I copy this, click that, do an Alt HVS or however you get to paste special, and tell Excel, yeah, I'm trying to paste some data onto this chart. I'm trying to paste a new series, not new points. I don't need more blue points up there. I'm trying to paste a new series. My data's in columns. I don't have my series names in the first row. I just have numbers in the first row. And my x-axis values are in the first column. So I'm going to click that. And I get the 3 points that I described, but I don't want to see points, so I'm going to right click, format that data series, choose a solid line, and now I have this goal line. Let's see, so if my goal had been a 7 instead of an 8, look how nicely that changes. Or a 6 instead of a 7, it moves along with the line there. I don't really need the orange dots, so I'm going to come back over here, click the series again, come back over here and say marker. Whoops, I just don't want any marker at all, so none. And as far as the shape of that line, so that's my goal line. Now for the next line, the value at risk, I know what the probability is. And since I'm entering it, I may be more or less optimistic, want to see a higher or lower downside. And now I need to calculate what number corresponds to the 0.05. And so for that, we'd use percentile dot inclusive. Look at the same array of data. And this time it's asking us for k, which really just means the 0.05. And again, if I want to start on the x-axis at this number, then I'll say the first point is going to be there, and 0, which is the x-axis. The second point is going to be this dot we just calculated. And the third point is going to be 0 on the x-axis and 0.05 on the y. Let's see if we can do the same thing. So let's copy those 6 cells, click, paste special. I don't want more blue points, or for that matter even more line on this black line. I want a new series, and I want my data is already in columns. I don't have series names in this first row, but I do have category X values in this first column. A little bit hard to see here, but let's do the same thing. Let's format that data series. To give it a solid line, and let's make that one red. This is at risk. And let's go to marker and say none. Now it's a little bit hard to see there. Let me zoom in on this chart. And we get the same kind of line here that goes from what would our worst possible outcome. And of course there's no worst possible outcome in some of these. So we always talk about like a 95% or a 5% worst possible outcome. And then come over to the line and go down. I think I'll do an example of this in a subsequent video here and recap everything. This has been a long video and it might be good to see it in a streamlined fashion.